Good morning, everyone. Good morning and sorry, welcome to the 35th ETP4HPC webinar. And by the way, it's still time to wish a happy new year to all of you. So happy new year, especially to our regular attendees because I recognize names each time. So it's really nice. So I'm Pascal. I'm ETP4HPC's communication manager. And my colleague Gabriela is also here to help run the show. For
Hello,
those of you who are
everybody.
not familiar with ETP4HPC, sorry, is there a problem? No? So for those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in HPC. And we are a private member of the EuroHPC JU, and our role is to propose research priorities for Europe in the area of HPC. And so this is exactly what we are going to present today with today's topic, which is our new SRA6. We'll have an introduction to this new SRA, and we will delve into a specific topic from this SRA system architecture. So before we start, a couple of practical information for you. So this webinar is recorded, and you will receive the link to the recording. This webinar is in listen-only mode, so you can't talk. But I mean, the attendees cannot talk, but you can interact with us nevertheless. You will be able to ask questions. There is a question tool here that you can use. And also you can download handouts. So today I have put 4 handouts for you. You can download today's slides directly in this handout section, materials section, I think it's called now. And I have put also the SRA6 itself and the white paper, the system architecture white paper that we are going to present today. So you can get them right here in the webinar. Concerning questions, sorry, I forgot to say you can submit questions at any time during the presentation using this questions panel, but we'll handle them at the end during the open discussion. So today's speakers, I will not read out their bios, but we have speakers today. Sai, he's our SRA leader
Yep.
at ETP4HPC. He also has a day
Hello.
job at Partech. He's a senior technologies and project manager at Partech. And we have Nico Mittensvey, who is from Megware, and Fabrizio Maguliani from E4. And Nico and Fabrizio were co-leaders for this system architecture white paper, together with Estela Suarez. Estela will not be here today, but we wanted to mention her also in the speakers as she was a very important contributor to this white paper. So agenda today, once I'm done, Sai will make an introduction to the SRA6, explaining how we prepared it. And then we will dive into system architecture with Fabrizio and Nico. And we'll take your questions at the end. So the webinar will be a little bit longer than usual because it's an important webinar. So that's it for me. I will hand over to Sai.
Thank you, Pascal. Good morning, everyone. Thanks a lot for joining. Let me
So Sai, now
share.
you should be able to share your slides.
Yeah, yeah. I'm just waiting for the share tab to show up. I think there's a bit.
Yeah, it takes a while. Sorry, guys.
No problem. So yeah, thanks a lot for joining. Maybe I'll just, as we are talking, just quickly introduce myself. I'm with the ETP for HPC in this context. I've been coordinating and leading this SRA6. So this is the first time I'm coordinating it, and I've taken over from Michael Marms, who used to lead the last 5 SRAs. So I used to be part of
Quite a
the storage and
challenge.
IO working group. Yes, it is, and now now it was an interesting challenge for me to get the whole SRA organized, and it was a lot of effort from the office, from the working group leaders, and the entire team. So I'm very pleased that we were able to release this SRA on time, and in time before the next multi-annual strategic plan from the Euro HPC REAG. So we are very excited to take this forward, and we'll see, how it's going to influence future programs. So with this in
Are
mind,
you sure
then
you're
Pascal,
sharing? Sorry.
not yet, Pascal. I'm just
Oh, okay.
waiting for. Yeah, now it's come up. Now it's come up.
Oh, okay.
Yeah. So let me share my screen. Okay. And I changed the setting to.
No, that's your
Okay.
notes you're sharing. Oh, now it's
Yeah.
good.
Now
Good.
it's good. Yeah. Okay. Great. So I've provided the introduction. So I'll just move to the next slide, which is so what's this philosophy of SRA6? So it's our strategic research agenda, and it's ETP4HPC's key output that's released approximately every 2 years, and this is the 6th version. And the idea is for this to be the go-to document to capture the state of advanced computing technology and innovation in Europe. And note that it's vendor neutral, so which is a very important thing to note. And the SRA6, these strategic research agendas are targeted towards the HPC community for them to know what's going on in this space, and also for decision makers and funding agencies to help them to structure the upcoming research and innovation plans and research agendas, etc. So what we have done for SRA6 is that in the past we just used to have a very big document, just one document which covers all the topics, and we got the feedback that it was very big and it was very unwieldy. So what we have done is that we have we now have a more concise SRA6 master, and then there's going to be these backing white papers that are released at the same time as the SRA6 master that has more information on the specific topics that are there in the master. So then we have the after we release the SRA6 master and the backing white papers at the same time, almost at the same time. Then we have, for the next 2 years, we are going to come up with these so-called agile white papers that are released every few weeks, every few months, and it incorporates more recent developments in the HPC community and discussions in an agile way. So this entire SRA6 process consists of these three sets of outcomes or deliverables: the master, the backing white papers, and the agile white papers. So what are the subjects that are covered in the master? So as you see, the focus is mainly on key recommendations for policymakers, um, and also for the community as well, and also provides the perspectives of HPC experts in Europe that we have worked very closely with while developing the SRA. So in the master, we cover mainly the summary of all the R&I recommendations from the various working groups or the white papers. And then we delve into our perspectives on HPC and AI explosion this time in the SRA6. And then we have our perspectives on post-exascale, and we have some of our thoughts on European exascale hardware initiatives and on European industrial HPC usage as well as European SMEs. So what are these white papers and these working groups? So every working groups, there is a corresponding white paper. So there are a total of there's going to be these 13 white papers corresponding to these research domains and thematic trends. So as you see, there are various research domains corresponding to various topics in HPC, like system architecture, which you're going to hear more about today. And we hope to cover all these research domains in upcoming webinars. And we also have these thematic trends as well, which are more cross-cutting topics and the trends that are actually percolating up in the last couple of years. We have AI and foundational models, energy efficiency and sustainability, and quantum and HPC. So what are covered in these backing white papers, which Fabrizio and Nico are going to walk you through today? So every white paper, for example, the system architecture, you have you go delve into more detail. You look into the state of the art in that specific subject and the upcoming challenges, and then you look into the post exascale vision and then the R&I recommendations in more detail corresponding to that topic. So I don't intend to go into a lot of detail here. So this is just to give you a flavor for the kind of recommendations at a very top level. And I'm just going to quickly point them out to you. Of course, you can have a separate webinar on each of these topics. So at the top level, what we have recommended is a strong data ecosystem in Europe for sharing of data across this Euro HPC Federation of Supercomputers. And we have recommended the development of a multi-year plan and roadmap in the area of AI for science in Europe, which is lacking. And we have also recommended innovation in the area of software and middleware to enable seamless integration of our upcoming federated HPC infrastructures and AI factories, the AI infrastructures. And we have also recommended that there's going to be better dissemination of Euro HPC AI initiatives into our wider HPC and AI community in Europe. And secondly, we have some recommendations in education and training where we recommend programs similar to EU Masters for HPC. We said that there needs to be corresponding programs for AI. And we have also pointed out that some of the areas are not well addressed in the work programs like data storage, data management, and IO. And that needs to take a bit more of a center stage, especially as we are starting to look at the importance of data in this whole AI explosion. And we have also spoken about and recommended adaptations to trend for lower precision arithmetic and more R&I in AI assisted code generation and adaptations of tools developed for the cloud for AI. And we have recommended the promotion of chiplet and interposer technology ecosystem in Europe. And also in the area of FPGA technologies, we have recommended how to address their large scale deployment and pushing for a more user friendly software ecosystem. And slightly on the political side, we also see that there's got to be better orchestration of national and EC funding and more flexibility in project timelines and budgets for all our research projects. And as you see, the global geopolitics is currently is very shaky, and we don't know what's going to happen. So there's got to be a very thorough and continuous assessment of the supply chain in view of these political developments globally. And for the EPI processor verticals, we say that there's got to be a better indication of the long-term funding levels, aided with some concrete commercial results. And in the area of the RISC-V, there's got to be a well-structured seeding and deployment plan now that we have the DARE framework partnership agreement active. And we also recommend that the modular supercomputing architecture that we have pioneered, Europe has pioneered that in many projects. So we recommend further development of that concept and enabling this Europe's unique excellence in that area. And in the area of SMEs, which might be interesting for many of you here, is that we have recommended financial management schemes with 100% reimbursement rates. Also, we said that there's got to be reservations for European SME participation in some procurement calls, and there's got to be more avenues for access to capital for HPC SMEs. Of course, Europe is not very strong on the venture capital front. It's not just the venture capital, but also access to all kinds of other capital as well, like debt instruments, etc. And we recommended enabling SMEs to file IPR applications across these fragmented national systems. So, so then quickly switching gears. So these are the leads for the different research domains that you see here, who have really put in a lot of effort over the last more than 1 year, along with the entire working groups. And I really would like to thank all of them. And I would also like to thank our partners from the Euro HPC Research and Innovation Advisory Group, and the Euro ETP4HPC industrial users, the SME working group, and also the project coordinators of some of these projects like UPEX, UPilot, EPI, eProcessor, and Red Sea, who have provided some inputs. And of course, it's been a great pleasure, of course, to work with my colleagues at the ETP4 office, which I also indicate here, who have actively contributed to the discussions and development of the SRA. And just thanks all to all the people that have worked with these leaders and developed the SRA, and also to the reviewers for this work. So that's it from my side. So I'll just stop sharing, and hopefully I've not taken too much time, Pascal. So we'll come back to any
No,
questions
we are
later.
doing fine. We are doing fine. We are
Okay,
right on time. So
good.
Nico, you should be able to share your slides now.
Yes, can you see them?
So, yes, we can see your slides. They are in slideshow mode. Everything is working fine. And Fabrizio, I think you're the one who starts on this presentation.
Sure. Thanks a lot, Pascal. And
Okay,
I'm really
floor is
excited
yours.
to, thanks. I'm really excited to be here and to talk to the community. I think that we have a great community in Europe, and these efforts, ETP, SRA6, are, from my point of view, a key factor for improving and growing more and more our knowledge about HPC and AI. I have also to say a big thank you to Nico and Stella, who have been helping a lot for this webinar. So Nico, next slide. I want just to frame what this call is going to be. I take the word from two gentlemen. One is Niels Bohr, and in this webinar, we are going to make a number of prediction, which, as we know, is especially difficult about the future. But at the same time, we are master of our destinies, because as a community, we can steer the European and worldwide technology and create our own roadmap towards sovereignty and autonomy. And this effort, I think, is totally commendable, and we all, as a community, have to pursue this objective to give Europe autonomy in terms of HPC and AI. With these words, I give the stage to Nico.
Yes, thank you, Fabrizio. And yeah, let's go right on the topic regarding the system architecture. So what I've listed here are some major points of the white paper, but of course, within the white paper, we also talk about some other aspects, but in the interest of time, I think those are the most important ones which I've listed here. So for starters, we will look into the heterogeneous integration of CPU, GPU, FPGAs, and other accelerators today. We will look into the storage and memory architecture, disaggregation of both of them, and also pooling strategies. We will look into the network design and what we can expect in the future. We will look in the resource management and how this can help in adapting for the workload distribution and also for the dynamic orchestration of resources which we have in our HPC clusters and AI systems. And we will also look into cooling solutions, as they are getting more and more important with the rising TDPs of the CPUs and also accelerators we are integrating in our clusters. And then to some extent also combined to this is the sustainability. So we will look in the energy efficiency, heat reuse, and also environmental considerations regarding, for example, hardware reuse, or how we can use hardware longer to don't waste too much resources on them. Right. So I think we can say that the system level heterogeneity is here to stay. If we look at the top 500, then 9 out of the top 10 systems use accelerators. The only outlier currently is the Fugaku supercomputer, which is using ARM CPUs. But this system is already some years old now, and I think within the next years, all of the top 10 systems will use accelerators in some fashion or another. And if you look at the green 500, then we see then all of the top 10 systems are using accelerators because, at least regarding the benchmarks used there, like the LIMPEC or the HPCG benchmark, they show that those accelerators that are used are really, really good at those algorithms and can push forward the performance of those benchmarks and therefore a lot of applications. Not all of them, but I think all of the major ones, and especially AI applications. And especially for those AI applications, we see that the GPUs are currently a stepping stone, but as a long-term solution, we see a more specialized or tailored hardware, especially since these GPUs are getting really, really energy intensive. So the current NVIDIA B200 systems or GPUs, they will need over 1 kilowatt per GPU. And this significantly impacts the system design regarding especially the cooling and, of course, power delivery, and also the architecture of the single system. And so what we think will happen is that in the future there will be more specialized hardware to either do AI training, for example, or AI inference, because with the development and this is the betterment of the AI models, many researchers will probably stick to inference and therefore don't need to train their own models anymore. All right, let's look at how we can build such an heterogeneous architecture within an HPC system. So this is something which, for example, Jülich did with their supercomputer. So they structured all the components, or the CPU, GPU, and FPGA and accelerator nodes within modules, and those modules are connected via a high-speed interface, for example, or currently InfiniBand, but this can also be CXL in the future, or also any other high-speed, low-latency fabric. And the special thing about this is that any application here can access those resources while running. So, for example, if we have an application which in the start needs to load a lot of data, of course, then you can load it very fast from the storage system and do this only on the CPU cluster. And then while they compute, they can switch or use some resources of the, for example, accelerator module. And this flexibility, this really helps in increasing the usage of the hardware which is there, and also increases the efficiency which the applications can use. And that being said, currently the interconnect technologies we see in the market are, of course, InfiniBand and NVLink for the connection between GPUs, and also Slingshot, and to some extent Ethernet, and they offer currently about 400 gigabit per second per link. But the really big problem is that they lack cross-compatibility between the networks, and therefore they require costly gateways between the networks. And this is one of the reasons the Ultra Ethernet Initiative has been founded, and they are searching for ways or trying to establish a standard where they optimize the Ethernet, especially for AI and HPC networking needs. So one of the major needs, of course, is the low latency, which in current Ethernet networks is not really achievable. But with this initiative, we hope to see an open standard where many vendors can contribute and also offer their own hardware. And so when we are building HPC or AI systems, we can choose from many vendors and are no longer vendor locked into, for example, InfiniBand. And what we also see is in development the photonics die-to-die interconnects. So currently we already have photonics within switches, but in the end we want chip-to-chip photonics to have really low power consumption and also latency in the network. And with that, we are coming to memory and storage. So in current systems, typically we have local NVMe, which can provide around about 10 gigabyte per second. And this is usually useful for smaller jobs where users read a lot of data again and again and again, for example, for AI training. So they can store the data locally on a node, and then in this way do not use the central parallel storage too much. So other users which really need the central storage are not hindered or slowed down by those training algorithms. And then we also have the central storage, which today can easily provide more than 1 terabyte per second bandwidth. And of course, this is only possible with the NVMe SSDs. But for cost-effective reasons, we also see that a lot of those storage architectures are using NVMe in a first tier, and then use HDDs in a second tier, and then even go to tape if, for example, the research data is no longer actively used, but mostly just for archive. And if like weeks or months later, some researchers need to access that data, then they can get it from the tape storage. And so it's very cost effective, but can also speed up to those terabytes per second bandwidth. And the data movement between those tiers typically is based on access patterns and file attributes. And then we have the memory. Currently, we see bandwidth of 400 gigabyte per second per CPU and 4 terabytes per second on the GPUs. And what we also have in our systems, traditional or still at the moment, is that we have a very static coupling. So we have those, let's say, 512 gigabytes in one node. And if I need more, then I have to find ways to distribute my algorithm over many nodes, or buy a bigger machine. So what we see here is that we will need in the future some flexibility regarding all the workloads that might need some more memory, especially for just a short amount of time. And with the upcoming CXL interconnect, this will be possible, so that we can pool memory resources from nodes together and allow those workloads to dynamically get more memory when they need it. Also, an important topic is the hardware-software co-design. So what we see in the market is that typically the hardware vendors are giving us great hardware with optimized, like say, registers or optimized hardware accelerators for certain kind of algorithms. So, for example, the HPL was a traditional optimizing target, and but the applications cannot really use it because they are memory constrained or any other constraints. And to be really efficient and have a reliability software architecture, we need to have more concentrated development together between the hardware and the software developers. But we see this trend, and we see that there is work being done on this. And what really helps is the continuous development and also continuous integration, which we see is rising within the HPC system all over Europe. And then also another topic, and a very important topic nowadays, is the efficient cooling and sustainability. So I think state of the art, we can say state of the art now is really direct liquid cooling. All the major top 10 HPC systems use liquid cooling to at least cool the GPUs and CPUs. And as I said, with the higher TDPs that are coming, there's no longer an option to even cool those chips with air. And another solution, what we see in the market, is immersion cooling. So there we take the whole system and put it into a non-conductive fluid, which then transports the heat to a heat exchanger. And this also works, but from experience, we see that the maintenance is a bit cumbersome because when you have to take out the compute nodes from the fluid, you still have this sticking somewhere, and yeah, it makes maintenance a bit harder, but still can be a viable option to cool our HPC systems. And another, let's say, method which is helping here is the two-phase cooling. So when you use water, this water stays liquid, but if we use a special liquid which can evaporate, then the heat which this fluid can then take out of the system, it's much higher. And this method can be used with immersion cooling or also with direct cooling methods, but it's still in development, especially for the direct liquid cooling method. And regarding sustainability, a major issue is, of course, that we have a lot of energy which we use to calculate and solve our problems within our HPC system, but then typically the heat is just evaporated into the air. And if we could use this heat to, for example, heat the university campus of the HPC system, then we can push our PUE factor of the whole data center below 1, and therefore reuse the heat, which otherwise would be just wasted. However, for such a heat reuse, we typically need outlet temperatures of the water or the fluid, which is then coming out of the data center, of at least higher than 40, preferable higher than 45 degrees centigrade. Yes, and with that being said, the key areas we see that we need to realize an efficient exascale computing HPC or AI system. One of the major key points is that we do hardware software co-design. So like I said, we really put together the hardware engineers and the software engineers, and then optimally create software which can really use the hardware, and the hardware guys know what the software does. We also need advanced interconnect technologies, higher bandwidth, of course, preferable lower latency. Also, this is very hard to achieve. And also the energy efficiency of the interconnects is very high topic, because there's still a lot of energy being used in the interconnect, and getting this energy out of the system currently is really difficult, because usually the for example switches are very tight integrated, and it's not so easy to get water or any other fluid in there. Then what we see is also the advanced memory architecture. So like I said, we need some memory disaggregation and pooling capabilities to be able to more flexible allocate memory resources. And the cooling technologies, we have direct liquid cooling, but there are still some optimizations to do, and maybe even switch to the two-phase fluids to be able to better get out the heat of the system and then reuse it in other like for example buildings. And of course, not only reusing the energy, but we also just need to reduce the energy consumption itself. And typically, this is of course achieved by optimizing the energy efficiency through more special tailored accelerators, dynamic workload management, resource partition, and of course also looking into the algorithms again and optimizing the algorithms for the hardware. And with that being said, I give over to Fabrizio again to talk about the upcoming challenges.
Thanks a lot, Nico. Great overview of what the state of the art is, and a very detailed analysis of where we are right now. Now we are entering in a sort of uncharted territories, because we have defined that is a number of challenges, and we expect that these are the most important challenges in the next years. Anyway, any update or disruption may happen anytime. The first challenge that we have identified is how to optimize the orchestration of resources, and be having a sort of framework for resiliency. We know that the future and the EuroHPC systems are a proof of that, will be geographically distributed, a number of cooperating resources across the member states. They are distributed in terms of geography. They have different architectures, as we know, and we don't, well, the workflow is in this moment unpredictable. It may be very high in some moment and very low in other. Therefore, we have to put in place an efficient system or framework to manage all these different systems in different locations, and the technologies that we have identified are mostly the MSA, the modular supercomputer architecture, using containers, and working on the federation of resources, as the recent EuroHPC procurement have been indicated. Nico, next slide. The other challenge, there, thanks, and how to integrate any new disruptive technologies which will pop out in the next years in the framework. As we know, as an examples, quantum computer have a different and incompatible programming model each other, and have a different timescale than traditional systems. Therefore, we have to analyze, to understand how to integrate these different systems, which are a sort of disruptive technology into the existing framework. And this requires to have a careful analysis of the trade-off among different parameters. So what kind of specific requirements are addressed by these different disruptive technologies, and why these requirements are not met by the current von Neumann system. And then time required to integrate these disruptive or new technologies into the workflow, and then what is the outcome or the influence of these disruptive technologies or on the current workflow. It does not make any sense to integrate the technology if it is not bringing any value to the overall efficiency and effectiveness of the solution. Next slide. The third one is to develop a modeling system for these new technologies and for the overall system, sort of having a digital twin of the system, but not only related to the hardware or software or infrastructure, but also of the workload that could bring very high return of investment, because this model may predict how to manage the resources, how to allocate different resources at the geographical scale, and how to maximize the outcome of the overall infrastructure. For this, we have to develop tailored modeling techniques, tools for getting the real number about the performance and the power consumption and the environmental status, and then understanding how to manage this interaction between all the heterogeneous component, and having a tight connection with all the involved parties, the stakeholders, which are basically the vendors of the infrastructure, the data centers managing it, the sysadmins, and the users. This is extremely important because we have to create a sort of collaboration among different partners to achieve a single, most important goal. Nico, next one. And the key component is having a clear focus on how to manage, monitor, and use energy efficiently. As Nico mentioned in his slide, the current trend is a skyrocketing increase of energy density and TDP. In the last year, we have seen this sort of unbounded race again to getting more and more power inside the system, mostly driven by the growth of the AI workflows. I'm not sure for how long we can cram energy consumption in the single node, and sooner or later, as Nico has been showing, we will hit the wall of the how much heat we can take away from the server. So we have to establish a sort of monitoring infrastructure of how the energy is used, and then make sure that we select the most suited technology for the single environment, which may be whatever is has been shown by Nikon in the previous slide, but to make sure that it is compatible and useful for the specific environment, and make sure that we power up, power down the most energy consumption devices when they are not used or they are partially used. And last but not least, deploy energy efficient domain specific accelerators. I think that the energy will be the key factor driving in this moment the evolution of the system, and it is going up and down the full scale. We have seen a couple of days ago the new system by a large GPU vendor, which is basically in this moment sitting in a small box. This is a trend that we have to take care most carefully, because it shows how to bring a high level of power, computational power, to the desktop, and at the same time trying to apply the same technologies to the large system. The next one. Having a approach of co-design is mandatory, because more and more we will have different specialized architecture in different environment, and we will have to make sure that we will be able to adopt evolving technologies. Therefore, we have to work all together and design the system taking into account the different feature. One of them is the failure rate of component. So having a more resilient infrastructure, try to mitigate the technical risk involved in the adoption of innovative technologies, and having a approach which is harmonizing different design constraints, a sort of a holistic approach where we take all the different components together to achieve the single goal, which is make sure that we do the job. And so design for maximizing performance, minimizing energy consumption, making sure that any component failure is not impacting or is impacting minimally the overall efficiency of the system, and then make sure that the end user have their results, at the same time not wasting energy or not having a large system unused. Next one, Nico, please. Last but not least, security. We have seen that the geopolitical situation is pointing out to having more and more threats coming from either organized, I have to be careful here, from organizations and or single threat coming from single man. We have to make sure that we want to have our system secure. We want to have our system making the right stuff when threat is arriving. At the same time, we cannot shut down all the system because of a single threat. So, and this is more and more important when we have a federated system working together and having authorization, authentication concern that we have to manage. So we have to, in this moment, we have to have security as a primary concern at the same level, at the same foot as the performance and energy. Next one, Nico. So we are getting to the end of this overview. Our planet is heating too much. So we have to make sure, and the resources are more and more scarce. Therefore, we have to focus on sustainability and recycling. Uh, we have seen that the A model and TDP are skyrocketing. At the same time, we have to make sure that we use as much as possible either renewable energies or low impact sources. Uh, it is, as Nico has been showing, we have to use heat for other objectives than throwing it into the air or into the water, and having a reuse approach for the materials that are used in the system in place of throwing them in some landfill. Uh, we may have a reward for a sustainable data center. So, at the same level of the top 500 in GRI 500, we may want to have a sustainable 500 for rewarding all the data centers or organizations which are approaching HPC as a sustainable business. Not only performance or performance per watt, but the overall infrastructure from power supply, power heating and cooling, and use of the components. And having these incentives for adopting sustainable practice is a way to support this sustainability and recycling effort. With, uh, with this slide, I think we are at the Q&A session. So I leave it to Pascal and Gabriella.
Okay, thank you. Thank you, Fabrizio. Thank you, Nico, for this presentation. So we already have questions, but I would just like to remind everyone that you can ask your questions in the GoToWebinar question panel. And Gabriela is copying the questions into the chat so everybody can see them. So I really encourage everyone, including our speakers, to go to chat and they will see all the questions. So let's start with what we have received for the moment. So the first question was from Somasheka Kulkarni. Sorry if I mispronounce your name. Thank you for the talk on this interesting topic regarding hardware-software co-design. Are there any EU-level projects where hardware experts collaborate with software developers working on frameworks like Cycle? I'm not sure how it's pronounced. SYCL, OpenCL, Sickle, OpenCL, etc. So who takes this question?
I volunteer.
You
Yes,
volunteer, Fabrizio? Go ahead.
yes. As far as I know, the projects where E4 is involved have a strong co-design approach. So the software developers are working side by side with the system integrators on the provider of infrastructure to achieve a strong co-design approach. Actually, we work, E4 works with the developers of compilers and libraries for designing a hardware infrastructure fitting the requirements of the software. Give you an example, which is much more important than 10,000 words. In the European Processor Initiative, there has been a very in-depth analysis of the structure and number of vectors for the scalar and vector accelerators, where we have been working together. The members of the consortium have been working together, and we have converged on a solution which is maximizing the performance on a large number of applications with the hardware constraints. So short reply to the question, yes, there are all the projects have mandated sort of having a co-design approach.
Yeah. Okay. Anything to add, Sai? No? Can we go on to
No,
the next
nothing
question?
from my side now. Thank you.
Okay. So thank you, Fabrizio, for this answer. So next question is from Dimitris Aspetakis. Thank you for the webinar. I'm really enjoying it. Thanks. You mentioned GPUs becoming increasingly more energy intensive and hence the projection for the need of custom AI accelerators. Do you possibly have any numbers on how much worse GPUs are compared to custom AI accelerators in efficiency metrics, GFLOPS, watts per watts, etc.? It would be nice if anyone has numbers handy for modern systems specifically. Do we have numbers?
So I unfortunately not. So there is currently also within the European Processor Initiative and also other projects, they are trying to develop inference accelerators based on RISC-V technology, which looks very promising. And there are also already some companies which ship such accelerators. But to be honest, I don't have the numbers ready, so maybe I can deliver them after the talk.
And
Okay.
if I chime in, I don't think that we should approach this issue in terms of worse or worseness. I think that GPUs have a specific standard commercial GPUs have a specific role in the market, as well as customized AI accelerators. So what we are saying here is the fact that we need both. It's not an exclusive or, is an and. So we need standard GPUs with all the power consumption they bring for some workloads, but we need also to complement them with custom specific accelerators where the workload mandates the use or requires the use of these accelerators. I mean, there is no point in shooting with an atomic bomb to a fly when we can use just the mouse squatter, if you understand what I mean.
Thank you, Fabrizio. Good point.
I don't know if it's
Okay.
the English, fly squatter.
I
I don't
think
know.
we all got the point. Question from Pierre-Yves Danet. So next question is about network and interconnect. This topic is addressing interconnection between supercomputing elements, but I guess that you also need interconnection between HPC centers and also with end users in order to feed the supercomputers and to deliver results. We also can expect in the near future HPC as a service that can be used by anyone. So in such a context, there is also a need to study external interconnection in order to provide a good quality. Is this question addressed in the SRA?
Yes. Okay,
Yeah, go ahead,
say, go
Nico.
on.
Yeah, go ahead, Nico, please. I'll add
Okay.
to your point. Go ahead.
Perfect. Okay, yeah, thank you. Good question. Actually, we go into the topic of federation within the white paper. We just didn't mention it here on the slides. So yes, we are looking into this. Of course, external interconnections are also dependent on external factors like the internet providers, but this is definitely something we are looking into. Right?
Yes, just to add to that, yes. So there's going to be an agile white paper that we're going to be working on Federation. And I think this topic would take, would get some good treatment there. So please stay tuned for the white paper on Federation, which is going to come up in the upcoming weeks and months. So you should have more, more of our perspectives there.
Okay, thank you. So next question is from Piero Lanucara. How do you see the rise in perf per watt of silicon devoted to low precision, both CPU and GPU hardware, with regard to FP64? This trend will continue, leading to the end of FP64 hardware support. Who wants to
I
comment on
take it.
that? You take
Ciao,
it,
Piero.
Fabrizio? Okay.
I take it. Ciao, Piero. The death of FP64 has been greatly exaggerated. Okay. FP64 is here to stay because there are some computation where double precision is mandatory for achieving the right convergence ratio. In the last years, mostly for architectural reasons, the developers, the hardware developers, have been going flat out on the 64-bit addressing register, software register, and hardware registers. I welcome the fact that we right now are more mindful about what kind of precision we need on the specific computation. So when we now understand what kind of precision we need for the single part, this is going to have a huge speed up in terms of hardware because we use the right components, and so we will have in the same infrastructure 64-bit components, 32 bits component, maybe less, FP8, something like that. Each of them is going to be used where it makes sense to use it. Okay, in place of going flat out on 64-bit FP, we are right now are able to define which is the best precision for the best application, and then send the right stuff to the right guy. So long life to FP64 will never die, but we all welcome different precision for the right applications. I keep my mouth shut now.
Don't. Okay. So I don't see any more questions. Piero says that he agrees. Yeah. Okay. Okay. So it's still time to ask questions. So dear attendees, you can still use the questions tool to ask your questions. But I would like, while waiting for any potential new question, I would like to thank Sai, Fabrizio, and Nico for their talks today. Is there anything you wanted to add, Sai, Fabrizio, Nico? Anything you would like to mention?
Well, if I may say, then I leave to Nick and Sai. We have we have our destiny in our hands in this moment as European guys. Your HPC, Praise, ChipsJU are making an awesome job, which requires our input. So let's take the destiny in our hands. Let's try to shape our destiny in order to make Europe as much autonomous and self-sufficient as we can. It is in our hands. It's not something coming from out. We have to we have to do that. It is in this moment a critical opportunity because we are one executive order away from not having the latest and greatest technology. And I'm sure that you know what I mean. So we have now to act, not to depend on external advice. I'm done.
Yeah.
Thank you,
Just,
Fabrizio. Sai.
yeah, just we have addressed a lot of topics in these SRA, different SRA white papers, and as you'll see. But what I would also request our listeners is when they come to the other webinars on other topics, and you see that some areas that are upcoming are not addressed, we would like to know, because we have this mechanism of where we can drill down into those upcoming topics in the next couple of years. I said as a mechanism called agile white papers, so we can drill more into it. So it's possible that there might have been some blind spots uh, in after you have gone through all the white papers, where we need to place some emphasis on. So we really welcome our listeners to give us some feedback saying that, hey, you guys have not addressed this topic, or there is something on the horizon that has not been looked at. So we would be really interested to know about your feedback on those kind of things. So yeah, that's it.
Nico, anything you wanted to add? You're the only one who. No?
Oh, thank you. I think everything has been said.
Okay. Thank you. Thank you, Nico. So, no questions coming in, Gabriela? No? No. Okay. So I think we will close for now. I would like to thank our audience for being here today. We had quite a large audience today. We are going to have more webinars about SRA6. The next one is at the end of January. It will be devoted to storage and IO and to programming models. And there are more webinars coming in February. So we will email everyone. I mean, we email all our webinar attendees to inform them of upcoming new webinars. So you will receive an invitation. Don't worry. And last point, ETP4HPC now is on Blue Sky. So if you are on Blue Sky, please follow us. And with that, I will say bye-bye. Bye-bye, everyone. Thank you for attending today, and I hope to talk to you on the 31st of January, of course. Bye.
Okay,
Bye,
see you all.
everybody.
See you
Thanks a lot.
everyone. Bye
Bye.
bye. Have a nice Friday. Bye.